Hello, the topic of my presentation is waste glass reuse in formed alkali-activated binder production, technical and environmental assessment. Let's start with the introduction part. In EU, CDW is now becoming a serious issue, and the waste glass is one of the main types of the CDW. But only a few studies investigate the use of 100% waste glass into the mixture. Our study focused on a formed alkali-activated glass, FAAG, based on the 100% of waste glass, and investigate the account of the forming agent, aluminium powder in this case. Then the test the optimal contact of the forming agent. The raw material we use in this study is sodium hydroxide, sodium silicate, aluminum powder, and waste glass. The chemical composition of waste glass is shown as below. And here is our mix design. We have three different levels of aluminum powder content: 10%, 20%, and 30%. The FAAG with 10% aluminum powder was selected because it has a similar mechanical strength and density with the 20% one. At the same time, it can reduce the amount of aluminum powder we used. Here we can see the pro structure of FAAG sample. You can see it has a closed network pro structure, which is really good. Here is mechanical property of the select FAAG sample. You can see from this figure, the compressive and the flexure strength is increasing with the growth of curing age. The strength of FAAG decreases with the gross water absorption, and with increasing immersing time, there's a reduction in the strength retention coefficient, which can be related to the additional water absorption, can further make capillary pores in FAAG, which leading to a lower mechanical performance. And for the 7-day values of the water absorption, it's a little bit higher, but it's still in the scope of the Chinese standard. According to XRD pattern, we can see the hump in FAAG shift forward between the 27 to 28 degree, which means there are some new geophases formed, which related to the process of the aluminum silicate. In view of that, we can see that the aluminum powder can not only work as the form agent, but also it is involved in the process of the geopolymerization. The FAAG was also compared with some commercial formed products. You can see from this figure, the FAAG has either lower thermal conductivity or higher compressed strength. When you compare with the foam glasses, you can see the foam glasses has a little bit better thermal insulation than the FAAG, but the FAAG has a much higher compressed strength than the commercial foamed glasses. Here is the environmental assessment of FAAG. In terms of carbon dioxide emission, you can see FAAG is 45% lower than the commercial products from the database. It's mainly because the PC in the manufacturing of the commercial products. And we all know that the production of the PC will release a large amount of the greenhouse gases. And we can also see if we can avoid the incineration and the land filling to deal with the waste glass, the environmental impact can be further reduced. In this term, we can see the carbon dioxide emission and the energy consumption they were both reduced in this case. Let's end with conclusion. Aluminum powder can not only work as a forming agent, but also working as a key part in geopolymerization. A low temperature upsealing of waste glass is feasible to produce formed glass with satisfied strength and thermal insulation. Second, the process structure of FAAG can affect the water and impact resistance. And although the water absorption of FAAG is high, the value is still in the scope of the requirement of the Chinese standard. And the FAAG in this study has a better performance than the commercial products in reducing the carbon dioxide emission and the damage to human health, ecosystem quality, and resources, which means it has a greater sustainability than the commercial one. Thanks for your listening.